Plastic has one of the strangest biographies of any material in modern life. It begins in the deep past, in fossil hydrocarbons pulled from the ground, then becomes packaging, bottles, trays, films, containers, toys, fibers, and thousands of other things we use for moments and discard for decades. That transformation feels one way. Oil becomes plastic. End of story. But in Japan, engineers have spent years asking a more provocative question. What if some of that journey could be reversed? What if waste plastic, especially the difficult mixed material that often ends up burned or discarded, could be broken down and turned back into oil-like feedstock again? It sounds like science fiction the first time you hear it, or like the kind of internet claim that collapses the moment you ask for specifics. But the idea is real. Japanese companies have built machines and industrial systems that can do exactly this. The real mystery is not whether the process exists, it is how it works, what it actually produces, and why a technology that sounds so miraculous still comes with serious limits. To understand why turning plastic back into oil is even possible, you have to start with a simple truth hidden in plain sight. Most plastic was born from hydrocarbons. It is not some alien material. It is a molecular rearrangement of substances that originally came from fossil fuels. That does not mean you can melt a bottle like butter and magically pour out clean gasoline. Reality is far more complicated than that. But it does mean the material already contains a carbon-rich energy structure that chemistry can attack, split, and reshape under the right conditions. In broad terms, that is the principle behind plastic-to-oil systems. Instead of trying to mechanically recycle every item back into the same form, these systems break plastic down into smaller hydrocarbon molecules that can be recovered as oils, gases, or chemical feedstocks. The best-known Japanese example for many people is the compact machine associated with Blest. On paper, it looks almost absurdly small for what it claims to do. This is not a giant refinery tower looming over an industrial port. It is a tabletop or compact system designed to demonstrate that household plastic can be converted into oil. According to the company's English product page, the machine processes roughly 0.7 to 1.0 kilograms per hour, with a recycle ratio of more than 80% over a roughly 3-hour run, depending on the plastic being used. In one official example, 400 grams of household plastic waste, including film-type materials such as food wrapping and plastic bags, produced 286 grams or about 380 milliliters of oil after about 3.5 hours of operation. Those numbers are specific enough to matter because they pull the idea out of fantasy and place it in the much more interesting world of constrained engineering. That word constrained is important. A machine like this does not prove that plastic waste has been solved. It proves something subtler. It shows that with controlled heat and the right reactor conditions, at least some types of plastic can be depolymerized or thermally decomposed into a liquid output that resembles an oil product. In other words, plastic is not only trash, it is also stored chemistry. The reason this feels so compelling on camera is that it reverses the emotional direction of waste. Throw something away and it seems finished. Feed it into a reactor, and suddenly the object begins to look unfinished instead, as if its first life as packaging was only one temporary chapter. But once you move beyond the tabletop demonstration, the story becomes much bigger and much more serious. Japan is not only experimenting with symbolic machines for schools, exhibitions, or decentralized demonstration. Industrial companies are building chemical recycling systems meant to process large volumes of difficult waste plastic and return the output to petrochemical supply chains. Idemitsu, for example, explains that it is working on oil chemical recycling in which collected used plastics are heated and decomposed using a catalytic cracking method called HICOP. The resulting product oil is described as equivalent to crude oil-derived feedstock, refined and decomposed at existing oil refining and petrochemical facilities to become chemical products again. The company says it has been constructing a recycling facility with a processing capacity of 20,000 tons per year near its Chiba complex, aiming for commercial operation in fiscal year 2025. That is not a gadget, that is industrial ambition. Mitsui Chemicals offers another revealing window into how this sector is evolving. In 2024, the company announced that it had sourced pyrolysis oil from plastic waste and fed it into a cracker at its Osaka works in order to produce and sell chemically recycled derivatives through a mass balance approach. That matters because it shows where the industry is trying to go. The goal is not simply to produce a dark liquid and stop there. The goal is to insert recovered hydrocarbon feedstock back into chemical production systems that already make materials such as ethylene, propylene, and polyolefins. In principle, that means waste plastic can become part of the raw material stream for new plastics and chemicals whose physical properties are equivalent to conventional products. The promise is not that yesterday's bag comes back as tomorrow's identical bag in some neat moral circle. The promise is that waste plastic can become chemical feedstock again, instead of being treated only as a burnable burden. Then there is the approach described by Mitsubishi Chemical Group in collaboration with INEOS. Their explanation goes beyond the phrase pyrolysis and highlights a process using supercritical water under high temperature and pressure. The company says this allows mixed waste plastics to be broken down into oil, with naphtha-equivalent fractions sent into chemical production and fuel-equivalent fractions sent into refining. Their plant at Ibaraki is described as one of the largest in Japan, with the capacity to chemically process 20,000 tons of waste plastics per year. But what makes their explanation especially valuable is its honesty about the trade-off. The company explicitly says, one challenge is that inducing the oil conversion reaction still requires a large amount of energy, even if the process is considered energy efficient compared with some alternatives. That single admission protects us from the laziest version of the story, because this is where plastic-to-oil videos often go wrong. They love the reveal and skip the accounting. A bag goes in, oil comes out, and viewers are invited to feel that waste has been defeated. But chemistry does not work on applause. Reactors need energy, systems need feedstock preparation, collection networks need to function reliably, sorting standards matter, contamination matters, economics matter. If plastic to oil is presented as a miracle, it becomes misleading. If it is presented as a tool with strengths and weaknesses, it becomes genuinely interesting. That weakness begins with the feed itself. Not all plastic behaves the same way. Some materials are much more suitable for oil conversion than others. Mixed streams can be tolerated better in chemical recycling than in some forms of mechanical recycling, which is one of the technology's real attractions. But mixed does not mean anything goes. Additives, chlorine-containing materials, dirt, moisture, food residue, and incompatible polymer types can complicate operations, lower yields, or force more pre-processing. Stable collection is also a huge challenge. Industrial plants are hungry systems. They do not just need technology, they need steady streams of material of acceptable quality, day after day, year after year. That is part engineering problem and part logistics problem. Then comes the public misunderstanding around the word oil itself. When people hear turns plastic back into oil, many imagine instant fuel, as if the machine directly manufactures pump-ready gasoline. Usually that is not the most accurate way to think about it. What comes out can be a mixture, an intermediate, an oil-equivalent product, or a feedstock that still has to move through refining or cracking before it becomes something broadly usable at scale. In a small demonstration setup, the liquid output proves chemical possibility. In an industrial system, the deeper value lies in re-entering petrochemical infrastructure. That distinction matters because it changes the meaning of success. The triumph is not that someone can light a lamp with a bottle's former life. The triumph is that difficult plastic waste might be pulled back upstream into materials manufacturing, instead of moving only downstream toward incinerators and landfills. And Japan has powerful reasons to care about that distinction. Government materials on the Plastic Resource Circulation Act frame the country's broader strategy around 3R plus renewable, meaning reduce, reuse, recycle, and renewable alternatives across the whole life cycle of plastics. The law pushes not only end-of-pipe waste handling, but also product design, collection, retailer behavior, and easier recycling systems. In other words, Japan's official direction is not build a magic machine and keep consuming however you want. It is a whole life cycle approach. That makes plastic to oil easier to place in its proper role. It is not the entire answer. It is one possible route inside a larger circulation strategy, especially for plastics that are harder to recycle mechanically. This wider context also explains why the technology attracts both excitement and suspicion. On the optimistic side, chemical recycling offers a route for contaminated or mixed plastics that might otherwise be burned. It can potentially produce high-quality outputs suitable for demanding applications. It may reduce dependence on some virgin fossil feedstock if enough waste can be redirected into circular systems. It can also use parts of existing petrochemical infrastructure rather than requiring an entirely new civilization to be built from scratch. For countries and companies already embedded in large refining and chemical networks, that compatibility is a major advantage. On the skeptical side, critics worry that the technology can become an excuse to keep producing too much plastic in the first place. If every waste problem is framed as something a reactor will handle later, then the pressure to reduce unnecessary packaging may weaken. There are also environmental accounting debates around emissions, energy intensity, and how much output really becomes new material rather than fuel. Even some companies promoting the technology acknowledge the energy burden, the need for better efficiency, and the importance of stable collection systems. That should tell you something. Serious advocates do not describe this as effortless. So why does the idea still feel so captivating? Because it offers one of the few waste stories that moves backward instead of forward. Most disposal systems are narratives of loss. You use, discard, compress, bury, or burn. Plastic to oil tells a narrative of reversal. The wrapper is not only residue. The bottle is not only clutter. The carbon inside these objects may still be redirected. For a civilization haunted by the permanence of plastic, that is an emotionally powerful thought. But the most mature way to look at Japan's plastic-to-oil technology is neither blind celebration nor cynical dismissal. It is to see it as a chemical recovery tool emerging inside a much larger struggle over how societies make, use, sort, redesign, and value materials. A small Blest Machine makes the principle visible. Industrial systems from companies like Idemitsu, Mitsui Chemicals, and Mitsubishi Chemical Group show how the principle scales into real infrastructure. Government policy shows that the technology is being framed inside broader resource circulation rather than standing alone as a silver bullet. And the companies themselves quietly admit what viral headlines often ignore. This takes energy, this takes engineering, and this only matters if the rest of the system around it improves too. There is a reason small plastic-to-oil machines spread so quickly in people's imaginations. They condense industrial chemistry into a shape the human brain can actually hold. Refineries are too large for intuition. Cracking towers, feedstock streams, catalysts, heat balances, and mass allocation systems all tend to disappear behind security fences and technical diagrams. But place a compact reactor on a table, feed in familiar scraps of packaging, and then show liquid collecting on the other side, and suddenly an invisible branch of chemistry becomes emotionally available. People feel like they are witnessing a secret being revealed. The ordinary wrapper in their hand turns out to have a second chemical identity waiting inside it. That feeling of reversal is powerful. It is also dangerous if it seduces us into believing that visibility equals simplicity. Because the tabletop story and the industrial story are related, but they are not identical. A small system proves a pathway. A large system has to prove a business, a supply chain, an emissions profile, and a stable end use for its outputs. Scale changes everything. Heat transfer changes. Contamination becomes more consequential. Feedstock contracts matter. Maintenance matters. Continuous operation matters. Safety matters. Even the meaning of success changes. For a demonstration device, success may mean that a few hundred grams of household plastic become measurable liquid oil. For a large plant, success means that tens of thousands of tons of waste can be handled consistently enough that refiners and chemical producers trust the resulting material in their systems. The emotional jump between those two worlds is bigger than most viral videos admit. This is why Japan's corporate efforts are so revealing. They show what happens after the headline. Once you move beyond, plastic becomes oil, you enter a landscape of process design and integration. Idemitsu's description of oil chemical recycling is really a story about reinserting recovered carbon into existing refining and petrochemical networks. Mitsui Chemicals' use of pyrolysis oil in a cracker is not about novelty for its own sake. It is about proving that chemically recycled feedstock can move through large industrial equipment and emerge as products with properties equivalent to conventional materials. Mitsubishi Chemical Group's discussion of supercritical water adds another layer, showing that companies are not all chasing one identical chemistry. They are exploring different process routes to solve the same broad problem: how to recover value from waste plastic that current systems handle poorly. That diversity matters because plastic itself is not one thing. People say the word plastic as if it names a single obedient substance, but in practice, it covers a whole family of materials with different behaviors, additives, melting points, contamination profiles, and risks. A clear PET bottle, a polyethylene bag, a polypropylene tray, a multi-layer pouch, and a composite consumer product do not behave the same way at end of life. Mechanical recycling works well for some streams when collection is clean and separation is strong. For others, the material degrades. The contamination becomes too high, or the mix becomes too messy for quality reuse. That is exactly the space where chemical recycling tries to justify itself. It is a technology designed not for the easiest plastics, but often for the awkward middle ground that conventional systems struggle to love. Even then, the path is not straightforward. A company can say it accepts mixed plastics, but mixed plastics remain a spectrum. There is a huge difference between a controlled mixture prepared for processing and the chaotic reality of post-consumer waste. Labels, inks, food residue, moisture, incompatible polymers, and chlorine-rich materials all force the system to work harder. Some of that difficulty shows up as pre-processing cost. Some of it shows up as lower yield. Some of it shows up as maintenance headaches, corrosion, unwanted byproducts, or stricter quality control requirements. The public often hears about the output and assumes the input must therefore be easy. Usually the opposite is true. And economics, for all the romance of reversal, are where technologies live or die. A process can be chemically elegant and commercially weak. It can work beautifully in pilot programs and struggle in real markets. Feedstock prices, collection costs, policy incentives, and demand all change. Even the credibility of mass balance claims can affect public and corporate adoption. None of this makes the technology fake, it makes it adult. Mature technologies survive not because they look magical, but because they perform under ordinary pressure. There is also a cultural reason Japan is such a compelling place for this story. The country has long lived with material constraints, energy insecurity concerns, dense industrial networks, and strong pressure to manage waste in limited space. OECD notes that incineration with energy recovery remains Japan's main municipal waste treatment mode, even as the country's per-person municipal waste generation has fallen well below the OECD average. That means Japan already has a sophisticated but imperfect waste system. Plastic-to-oil technologies emerge inside that reality, not outside it. They are part of a national search for better circulation routes in a country that cannot casually assume infinite landfill space or infinite tolerance for waste. The context is not utopian. It is practical, industrial, and urgent. That urgency helps explain why the title of this story feels almost cinematic. Japan built a machine that turns plastic back into oil. Sounds like an invention from the future dropped into the present. But in truth, it may be better understood as a machine built because the present became impossible to ignore. Plastic waste grew too large, recycling limits became too visible, and old disposal habits became too expensive environmentally and politically. Reversal stopped sounding eccentric and started sounding necessary. The machine is exciting because it appears to undo damage. The system around it is serious because it knows undoing damage is harder than making promises. In other words, Japan did build machines that can turn plastic back into oil. That statement is true. But the real story is better than the headline. It is not a fantasy where waste vanishes into a miracle box. It is a story about chemistry pushing against the limits of disposal, about engineers trying to recover value from one of the modern world's most troublesome materials, and about a country exploring how to move plastic from a one-way culture towards something more circular, even if that circle is still incomplete. The machine is real. The reversal is real. The challenge is real. It matters.